how a practitioner who's going to do their first organizational development study, and they're going to try to not do the usual null hypothesis and the p-value, et cetera. I put in a link to that program you recommended in the chat. Can you guide, and then people get access? So that would be very
That'll
helpful.
work too.
Okay.
Yeah. So anyone who wants to do this can have it.
Thank you.
I have one question if you have time.
Go ahead.
Interesting. I mean, this is excellent information for anybody who's trying to do things better, make better decisions. That's a big passion of mine, and that's why I work with Olivia so much on how do we help people make better decisions in life. Well, with the influence of data scientists consulting major corporations all the time, I wonder if they are like open to these kind of concepts to do better data scientist consultations. Like I feel like if you had conversation with them to help them be better consultants.
Yeah, it's a good question. I have good news and bad news about that. The good news is that people in especially in statistical areas are more and more seeing that this is a much better way to go. Mm-hmm. But remember, this is very new. The paper is still in press.
Yeah, that's what I figured.
Yeah, and in fact, Sabine and I have a joke about it, which is that the top journals are happy to accept my papers as long as they don't have to publish them.
I appreciate it.
So the good news is that among the statistically or mathematically well-informed, this is becoming much more popular. The bad news is that most are not that well-informed. And so my guess is that when you talk to your consultants, they will not know what you're talking about at first until you explain it.
Okay. All right. That makes sense. Thank you, David.
My pleasure. Amin, I think you have a hand up.
Yes, I'm going to ask you a provoking kind of question, okay? I'm a student, a former entrepreneur transitioning to academia, and I've done applied mathematics in image processing, okay? So for me, I was always, when we talk about statistics, for me, it's not mathematics, you know what I mean? Because it's not rational as soon as we talk and things like that. And I was wondering, okay, did you heard about wavelet analysis, about statistics, which is much more about non-stationary data and things like that, okay? And why I'm telling you that, it is because for me, example in business, we do a lot of statistics to try to find out the right decision, okay, to make the right decision. So you say, but intuition, you know, all best decisions sometimes doesn't go with statistic, and even sometimes in politics, sometimes statistic is wrong. You know what I mean? When I say statistic under brackets, I'm including, okay, probabilities, of course. Thank you very much.
Right. So I think that given what you just said, I'm guessing you will like what I'm about to say, which is that a big advantage of these gain probability diagrams is that you can assign your own subjective utility to the different outcomes, right? And from there, you can calculate subjective expected utility and then make a reasonably rational decision. Or alternatively, if maybe you have a different decision rule, maybe you want to minimize the maximum harm or maximize the minimum gain, or whatever your decision rule is, you could use this as a preliminary step to making a decision based on A, your assignments of values to the different probabilities, and B, the sort of decision rule you want to use.
Thank you for that question. I'm going to move on to Olivia. I'm not going to have a rejoinder at this time. Go ahead, Olivia.
Yeah, I want to just thank you. I really enjoyed this. I spent 35 years as a data scientist, but I was doing it in a marketing context. And so I was trying to figure out I mostly did, and what I specialized in was logistic regression for predicting if somebody was going to respond to an offer or default on their payment, whatever. And so I was contrasting it because I've written a couple books and I would talk about descriptive statistics and how important it is to understand your population. So I haven't studied it for a while, so I really want to dive in because a lot of your stuff made sense, but I didn't quite follow it all. So I just want to say for people who have no statistics background, if you feel lost, don't worry, because even with my statistics background, I'm still comprehending it. But I wanted to ask if you see that the value of p-values would make sense in a, say, direct marketing context or even a risk analysis where you're not doing any kind of intervention to change people. You just want to know if they're going to respond or not. And you don't care to go and give them help or coach them to be better responders. Does that make sense? So,
Yeah.
we did like millions of records and and just came up with yes or no answers. So yeah, I'd love your feedback.
Okay, so actually, your question is reminiscent to one of David's questions that I hadn't answered, and so I'm going to answer both right now. Olivia, where are you? Your picture just changed on me.
Oh, here.
Oh,
Yeah,
there you are. Thanks for waving. Okay.
Yeah.
So let's talk about significance testing. In statistics textbooks, they'll tell you that you're assuming the null hypothesis, and your p-value is conditioned on the null hypothesis. The null hypothesis is that there's no effect. However, your statistics books are not telling you the truth. They're correct in the sense that you are assuming no effect, but they're incorrect in soft pedaling the many additional assumptions you're making that you don't know you're making. For example, you're assuming that you have randomly and independently sampled from your population. I'm a journal editor, which means I've read many, many thousands of studies. I have yet to read one where this assumption is true. And there are countless other assumptions that I don't need to go into. Just take my word for it, there are lots of them. And I would say that the probability that all of the assumptions are true is about 0. So once you see that the statistical model is wrong and that your p-value is conditioned not just on the null hypothesis, but rather on the null hypothesis plus a whole bunch of other assumptions which are tantamount to certain to be wrong, it should be clear that the p-value is meaningless.
Okay, now we're going to take more questions, and Olivia, you could come back with another question. I want to get some more questions, particularly on organizational development and kinds of measures we use. So can we get another question, please?
I have a very naive question.
Go ahead, Carol. And I'm sure it's not naive. Go ahead.
We have many people, new doc students, who are struggling from being practitioners to have to do either quant or qual research in the context of organizational development. And some of them are doing straight statistics, and this all makes a lot of sense in its high level, not detailed. And for the qualitative students, their eyes will glaze over and it will make no sense. And the statistics teacher will say, if they're on a qualitative committee, why don't you have a control group? And the qual people will say, we don't have control groups. And you've just opened the door for me to ask that question in a non-charged environment. If it's inappropriate, I'll take it offline.
Oh, I think it's a great question. In fact, even though I'm not a qualitative researcher, I have published exactly one paper in a qualitative journal. And the reason is because one morning I actually got upset at my colleagues for making fun of qualitative researchers. Why were they making fun of qualitative researchers? Well, because qualitative researchers don't have numbers, so they can't do a significance test. Whereas my position was that since they shouldn't be doing a significance test anyway, we are criticizing qualitative researchers for failing to do that which they shouldn't be doing anyhow. And so I wrote a paper and sent it to the main qualitative psychology journal, and they loved it, published it, and it's one of the most highly cited papers in that journal. So I agree with the premise of your question, which is that you have to ask first, what's the point of the study before you start saying, well, why don't you do this? Why don't you do that? Why don't you do the other thing? The first thing you have to ask is, why are you doing the study in the first place? And if the study is one where a certain technique is helpful, great, use the technique. If the study is one where it is not useful, then don't. For example, if you're just collecting exploratory data to try to figure out a basis on which to start theorizing, a qualitative study that doesn't have control groups makes some sense. So, Carol, did I answer your question?
I wish you'd shouted from the highest people that,
Yeah, we will. We got it on film. Thank you, Carol. We're going to move on to Jack. And then Amin, I want you to stay on in organizational development, please, with your question. Go ahead, Jack.
Thank you, David. And David Trafimow, thank you so much for your presentation. We've all been looking forward to today. I am a non-statistics person, but I am a coach. So I'm going to ask you a question from a coaching standpoint. Given the statistical methodologies that are currently out there, and that organizational development decision makers on the buyer side, on the company side, and the organization side, I'm wanting to frame this in a macro way. Given the methodologies that are out there now and the new methodologies that you and your team are bringing in, what is the difference in what you bring overall, as a general question, the difference in the integrity of your methodology, and how soon and how well can that be sold and communicated effectively to the people on the OD side that need to hear this new methodology and really wrap their arms around it and take it on?
Okay, so that's a lot of questions. I'll try to answer. I'll try to remember them all in my answer. What I would say is this: if you're interested in what I'm going to make up a term because I suspect there is no such term. If you're interested in what I'm going to call evidence-based coaching, then you'd actually want to try out different methods of coaching and compare them against each other in a study to see what works the best. And in that event, I think I've shown you that if you go my way, you'll get much better, much more precise, and much more correct answers than if you do it the normal way. So that's the first part of your question, and that part should be an easy sell. I would hope. We'll get David Boji to sell it. The next part is, and this partly gets at something that Carol mentioned also, which is that people freak out when they hear the word number or statistics. One of the neat things is that, at least in my opinion, the reason many people find statistics so impossible is because at base it is illogical. And to see that, and let me be really clear about it, there is a basic illogic behind significance testing that I didn't talk about, which is, think about it. If the null hypothesis is true, my finding is unlikely. The p-value is interpreted as my finding is unlikely, therefore the null hypothesis isn't true. Now that's basically logically invalid, and I think that smart people can stumble over having to accept a logically invalid starting point, right? To see it really quickly, what's the probability of being president if you're an American? A small number. What's the probability of being American if you're president? According to the Constitution, well, you know the answer. So you have very different numbers, which shows the basically illogical foundation point. And I think that's why people find it difficult. You saw those programs, the APP programs will take you all of 15 seconds to learn how to use. The GP might take you 5 minutes rather than 15 seconds, but 5 minutes isn't much. So
Right.
I would think that it's a much easier way to go just practically, not just in terms of correctness or scientific value.
Yeah. Yeah. Thank you.
Oh,
Was that
thank
everything?
you.
That's pretty much everything I asked, I think. Yeah.
Good
Okay,
job.
good.
Good
Thank
job,
you.
Jack. So while we're waiting for more questions, I'll ask one. So David Trafimow,
I think Brandy has a question.
I can't see the hand up, so could you please raise your hand if you're going to write a
She
question?
is. She's waving it. And
I
Brandy,
can't-
go ahead.
But I can't see that. Okay. Okay, let me see.
Brandy, you're muted.
I know, I'm okay. Can you hear me?
Yeah, go ahead.
can now.
Go ahead now, and
Great.
thank you.
I do work with neurofeedback, and this is very interesting because if you look at the research on neurofeedback, it's all over the place. And talk about, I would say, a population that can be different in each case. I think this is what we see in neurofeedback. So we'd use a QEEG analysis, right? A quantitative electroencephalographic digital analysis when a person comes in, and you can see changes, and there's an analysis of what each brain wave dominance is in different regions of the brain, right? So it's a very interesting thing. So I'm wondering if just one subject, if you can, what would you do with one subject who, using the changes in their quantitative electrical encephalographic pre and post tests would be, how would you be able to get a significant analysis with that
Well,
with APP?
I think you could, but rather than using the person as the unit of analysis,
Mhm.
you'd have to use the trial as the unit of analysis. So you could compare, let's say you had 1,000 trials before and 1,000 trials after. You could compare across trials rather than across people, and you could still use GP analysis.
So you would use variety of different people because you'd have different trials of various.
Well, it depends. You in your example, you said one person, and I'm saying you could do it for one person if you had a sufficient number of trials.
Okay,
How many trials do you need? You would use the APP to figure that out.
I see. Great. I think that's great. Thank you.
Oh, that
You're
was
welcome.
a great question. I appreciate it. It's about coaching and consulting.
Well, David, you may not know Brandy, but she's not only beautiful, but she always asks great questions.
Okay, David. David,
Adore
let me
you.
ask another question. I don't know if it'll be great, but just to follow on to what Brandy's saying. So a lot of studies will be qualitative in organizational development, but they'll have a measure of, say, satisfaction with the study or something like that. And they'll do a pre-survey and a post-survey, maybe on the value of this in their own organization, for example. So they might get some pre and post, very simple 7-point scales or something. How would they use gain analysis or other approaches you've mentioned today.
Yeah. I didn't give any examples of it, but um, for all of the programs, we have matched sample versions of it. So pre-test, post-test would be matched sample because it's the same people completing the pre-test and the post-test. So you would use one of the matched sample programs, and you could construct a gain probability diagram just like the ones you've already seen. You would just use a slightly different program. Sorry, David, you're muted, so
Thanks
I
for
can't hear
the
you.
answer. I appreciate it because I think a lot of people starting out are doing fairly lots of interviews with, say, a dozen people, and they maybe have a pre and post test as part of that. Other thing that happens, axiology measures are very big, and I've talked to you about it before. Ranking of 16 items twice. And a lot of people at the conference I went to in organizational development are using that scale. And my friend Tojo Chachinkari has the appreciative intelligence scale that's been validated, and he has a validation study published. So that's an example of two scales. One's rank order, one is a set of 7-point scales that can be used in organizational development studies. I wonder if you would say what somebody starting out could do with your approach, say, to amplify some of those scales with a little bit different interpretation. I know you've shown me.
Yeah, I see what you're asking. Let me, to answer your question, I have to refer to some other work. I have another paper in press at Psychological Methods that's about measurement. And one of the shocking things that I can prove mathematically is that the better your items correlate with each other, the worse you can predict anything. Just digest that for a second, right? What have we done ever since the beginning of social sciences? You've been told you want your you want your items to correlate with each other, so you have good reliability, and so you can predict well. And I'm telling you that all of that is incorrect. It turns out that you're actually much better off if you separate, I call it unamalgamate your tests, so that each item is entered separately into a multiple regression equation. And you will always predict at least as well or better, whatever your criterion is, doing it my way than doing it the normal way. So, David, given all of that, the first thing I would suggest for a beginning person is first look at the individual items themselves without assuming that they measure the same thing.
Okay. That's a really good answer, and I appreciate it. It's going to be very helpful. Tom Lemke has his hand up. Go ahead, Tom.
Thank you, David. This is really interesting. Having spent most of my life in direct response marketing, a lot of statistical analysis similar to what Olivia was talking about, but I'm not a statistician, so I'll start with that. I'm a marketing person. And as we look at this OD, and I'm really focused on gratitude these days, and we know that gratitude can be measured scientifically by brainwave analysis, that sort of thing. But it is a qualitative trait. So when you go in and talk to a company about changing your culture and getting people to be more grateful, we know that companies that are gratitude-led outperform financially ones that are not. So there's a big opportunity there. The question I have is, how would you use this to apply to the situation of gratitude analysis, or just the whole idea there? Thank you.
Okay, so Tom, if I'm understanding your question correctly, it's possible to categorize organizations as being one way or the other. And so I'm going to start with that in answering your question. I'm just going to take your word on that. It seems to me you could actually get much better information. Right now, I'm guessing what the research is, based on what you said, is that mean money made by the company is higher for gratitude-based ones than for monetary-based ones. However, with GP analysis, you could actually say, well, what's the probability of being, $100 better off, or $200 better off, or, $3 million better off? You can actually figure out and have good estimates of all of those. And so you would get much better information from a gain probability diagram than you're currently getting.
That's great.
Does that make sense?
Yes, absolutely. Perfect. Thank you.
You're very welcome.
Amin, go ahead. I didn't see your hand before. Go ahead, Amin. Do you still have your hand up?
Yeah, yes, I'm just
And we'll
wondering.
go to Ken. Thank you very much.
Yes, so I'll try to be much more focused and want to say to Dr. David, how are you able to discuss or to converse with positivists when you tell them that the null hypothesis it is a wrong-headed approach to science, as he said, Dr. David as well? How are you able, this kind of, it could be sensitive. I don't know how you manage that.
Yeah. Okay. So let's talk about
Go ahead,
positivism
David.
for. Yeah.
I hope it is the right question, David, Dr. David.
That is a good
Hey,
question, and I acknowledge it. Thank you. David Trafimow.
I'm happy with, if you had asked me, to apply it to ancient Assyria, I'd be happy to do it. So it doesn't matter. I'm happy with wherever the conversation goes. But about positivism, I think let's first be clear on what positivism is, because I think a lot of people don't have it right. So what happened back in the old days when people became clear that Newton had it wrong, the question that people asked themselves, especially in the Vienna Circle, but not only in the Vienna Circle, was, how could we have been so wrong? I mean, that's a big deal, right? How could we have been so wrong? And the answer at the time seemed to be, well, if we didn't depend so much on our theories and depended much more on what we can observe, then we'd be better off. Then we wouldn't make these mistakes. And so positivism was eventually developed into logical positivism and is highly related to operationalism. All those things you've heard of, really comes down to this idea of de-emphasizing theory. However, they ran into a problem, which was that they quickly realized that theories are necessary. I'll give you a really silly example. Suppose I have a container of water. I could boil it on my range. I could put it over a Bunsen burner. I could put it over my campfire. And the problem is, once you don't have theory, each of these ways of boiling the water would be considered operationally different, which is a blatant problem with positivism. And these were really smart people. They saw that this was a blatantly obvious problem, right? And so then they started saying, well, okay, yeah, we admit you got to have theories, but you have to tie them to your observations. And so then positivism merged into this concept that that you have to connect the theory to the operations. But that doesn't work well either if you think about it carefully, because well, I'll take an example. I'll take a psychology example because I'm used to that. Let's say you want to measure attitudes towards seatbelts, towards using seatbelts. Well, okay. Suppose one researcher measures it with a reasonable question, and a second researcher measures it with how much do you like chocolate? Now, common sense says that the chocolate item is blatantly invalid. It has nothing to do with attitudes towards seatbelts. However, if you take a strict operationalist perspective, where you define your theoretical concept by what you measure, then your chocolate measure automatically becomes valid because you have defined it so. And so this is a terrible weakness in positivism, and that's why I think you will have a very hard time finding a philosophically sophisticated person who accepts positivism. So I think the way to argue with a positivist is to just go to their basic assumptions and point out that they don't work. And you won't find you will not find a physicist anywhere who is a positivist, would be my guess. I think it'd be really hard to find such an entity.
Thank you.
Does that help?
Yeah, thank you. Thank you.
You're very welcome. I think Ken Long has
Ken
a
Long, go
hand up.
ahead.
Yeah,
Thank you.
yeah, Mike, check. You hear me okay?
I hear you.
Okay, so I want to propose a hypothesis for where this insight into statistics aligns with qualitative research for business opportunity in the following way. Most statistics in business have been used to try to find how a very small difference with a lot of scale can lead to profit. It assumes that people are like other people everywhere, and if I find a little bit of an advantage, I can scale that with a large business. What I think what your statistics show is that we are more unalike than alike in every possible way. So here's in business what I have to do, and in trading and in entrepreneurship. I have to find value where nobody else has found it. So what I'm actually searching for is deviation from some norm, which your stats will smoke out very quickly. And the stranger that is, the less data that I need to have confidence that there's something unusual here. So, for example, when Monty is going to show us how we all measure out on these different dimensions of uniqueness that he has, you can argue using the research of Angus Fletcher from Ohio State for creativity that the greater divergence you have at the start point, the greater probability that you're going to create something unusual and potentially valuable out of your collaboration. So if I have three divergent people, but who share the axiology of service to others, I have a basis for genuine, honest collaboration, but I also have the divergence that's going to create the new opportunities that haven't been seen before. And so what I need is not a measure of how similar I am to the population, but I need measures that show how divergent I am. And then I know that I'm in the gold enriched ground in which I just have to find the gold that is the unique combination of our divergences. So what this is going to help us do is take divergent people, which we are, and find ways to help other groups discover their own unique value propositions through the use of axiology, narrative inquiry, and qualitative research. So I think this is starting at the other end of all the assumptions that you just showed are wrong. It says if you take the opposite of all those assumptions, you're starting with the ideas that people are different and that this is a unique moment and that it doesn't necessarily scale, but this is a good place to start to find something new and of value. So I think there's a lot of power in uncovering opportunities that have been rounding error before, things that have been ignored. So I'm really excited by the work you did. I hope.
Oh, thanks. And you might be interested to know that in a paper I recently submitted, it's a revision for psychological methods. I made a rather similar point, which is it turns out you can use gain probability diagrams to interpret correlation coefficients. And I made the point that one advantage of doing that is that sometimes you'll see really huge differences at the edges of the diagram that you don't see in the middle of the diagram, which imply theoretical possibilities for
let me give you the exact example in the world of risk management and institutional investing. All of the models that assume normal distributions in financial markets are build their diversification portfolios on the basis of correlation coefficients most of the time. And so they build what they think is a divergent model until you really need the divergence. And then when the market starts collapsing, all the correlations go to 1.0. And now what you thought was diversification so that you could leverage has now become your fatal flaw. So it's at the margin, on the fat tails, where the correlation models break down, is where the genuine opportunities occur. So I would confirm your insight with practical examples. I make a living doing that.
Cool. Thank you.
Thank you. And thank you, David Trafimow. We're going to wrap up now because we've run out of our time. And I just want to, before we thank David, I just want to say in the chat, I put a meeting for tomorrow. I'm going to talk about Aristotle and horse sense. And the link is there. I'll also send this out to everybody after today. On the 21st, our next guest for the Monday session is going to be Monty Miller and his group. And Vujade is the name of their instrument that they're going to talk about in its use in organizational development. And I encourage you to take the instrument before. The link is in the chat, and I'll send it after the meeting, because we will be showing live the analysis of the group, of the steering group of Growth OD, and anybody else that submits and answers to the survey to Vujade. That'll be included in the filming that we're going to do next week. So now I just want to thank you, David Trafimow, and have everybody online give a one sentence or so on gratitude to David Trafimow. And David, I'm grateful. I've learned more today than in all the dinners. And I think it's because I was concentrating on my wife and maybe not on what you were saying, because she's very beautiful. So I'll throw that in. But I am grateful. And could we each go in turn and do that? Or should I'd like everybody to express gratitude to David, and then we're going to sign off. Thank you.
I'd be happy to go to start it. Yeah, David, thank you so much for your presentation. I'm not anywhere near a data scientist or a statistician, but as a coach, I can integrate it within the understanding of the whole organization. And in gratitude, David Boji, I want to say that I'm starting to see how we all come together. And when I go out and talk to a potential client, I have all of you on my shoulders to bring into my team to a possible connection and engagement. Thank you. I'll pass it over to Ken Long.
Well, I'm grateful for David Trafimow's courage in challenging mathematical traditions and simplified interpretations, looking at the actual numbers and what they mean. So thanks for your courage.
I'll jump in. This is Doug Breckenridge.
Yeah.
I'm Lenny Miller's business partner, by the way, so I'll be chatting with hopefully all of you next week. So I invite you to please take the survey and reach out to me so that we can get you into the Growth OD team beforehand. But David, I wish I knew you 9 years ago. It was eerie to look at all the graphs you had coming up, because I was challenged with all these same kinds of statistical analysis. And we will definitely be now reapplying and bringing all this into Vujade and our Cabo platform, because it just made total sense. It was the same challenges I was facing as I've developed, and my team has helped develop this platform, and the kinds of things we were hearing from statisticians. It's like, that doesn't make sense. Well, what you're saying doesn't make sense. So I really look forward to applying these tools. I can't wait. Great presentation. Thank you.
Thank you.
I'll go. Just want to thank you. I agree with everything that's been said, and I'm so excited to be able to take what you're doing into organizations and really understand not on the average, but all those nuances and a way to measure it. So thank you.
You're very welcome.
Thank you, David. I just say, I think it's so great that help people make a better decisions in life, helps them live a better life. And you're giving them tools to do that. Correlation does not equal causation, and so many people get confused that way. And it's just kind of like the ahas were so plentiful, and there's so much to appreciate as I go back through my notes. So thanks again, David.
You're very welcome.
Mhm.
Brandy?
Anyway, this is such an exciting work you're doing. I think it's going to bring about so many new ways of asking questions and coming up with different ways to address them and to help whatever subject matter you're dealing with. So I have 100,000 questions, so I can't do it here. Okay, love you.
I sense a dinner coming.
Yeah, this is a good dinner. This is a dinner, a good one. Okay, thank you.
Tom Lemke has his hand up. Go ahead, Tom.
David, thank you. This was very enlightening, and I agree with so many of the other comments that it's very difficult to get the world to change, and you're a pioneer doing this, and it's wonderful, and I appreciate the opportunity to get to know you a little bit. So thank you so much for sharing all your wisdom. And I will try to apply it into the gratitude space, so that'll be fun.
I'll pass it to Joy.
And I'm Joy Harris, and I'm in Ohio, so I'm not going to be able to come to that dinner, but I am so grateful that we have the technology to meet virtually like this, and that I'm able to be introduced to so many great minds and so many philosophies and methods and ways of communicating. And I am so appreciative of the talk that we had today. So I've always loved Miss Sabine, but now I have grown to love David Trafimow as well. So thank you so much for being here.
My pleasure, but look,
yeah.
But let me point out that Sabine is still the better one.
Well, let's hear from Sabine. What are you grateful for today, Sabine?
I am grateful for all of you, and I admit that I understand only a fraction of all of this, but I also feel that each time I hear it, I understand just a tiny bit more, and over time, I might get there. I appreciate, actually, I have to say, I really appreciate this space. And as Joyce said, I appreciate us meeting like this and coming from different backgrounds. And I think this is so wonderful. And Joy, thank you. I love the writing group.
Okay. Jim Rogers, you've been patient listening to this as a photographer, artist of renown. What are you grateful for today?
Well, I'm grateful for new information that I barely understand, but I believe that it might lead to helping make better decisions in different situations. And so I'm grateful for that opportunity to learn a little bit today. You're muted, David.
I was trying to put you up here with me. Let's get the view thing done. Okay. So if you look at Jim Rogers, that's one of his photography masterpieces. One of the things that I think David Trafimow's methodology could do for you is we could measure some people looking at those particular kinds of fireworks, I call them, and some other kinds of landscapes, and see what people are more interested in, do a gain analysis, I think. In other words, it has practical utility to you. I wanted to let you know that. And
Right.
I'm going to turn to Amin. What are you thankful for? I think want to hear from you.
So there is a great thinker, a visionaire by the name of Simon Sinek. He said, "Life is beautiful is not because of the people about what we do, things or what we see. It is because of the people we met." So I just want to thank everyone, and particularly Dr. David. So that simply put, Dr. David as well. Let's keep in contact via LinkedIn too. So thank you very much. It's very grateful.
Okay, we will do that. And we have here one more person. And let me see. I was identifying him on the screen. Paul, where's Paul?
I'm here.
There you are. Paul, wrap this up for us today. We all got to go to lunch now.
Right, including me. I echo so much of what everybody said here. Two things. I detect by being here that an answer or a response to the chaos in which the United States is enveloped. This is an answer. People keep looking, say, how are we going to figure this out? What do we need to do? We need a plan. I feel like I am sitting in the middle of the plan. It makes no sense because there is no way to say, oh, where will this go? But thanks to David T., a place where this can go is like, holy shit. Wow. And the other thing that I wanted to say is in terms of evolution, what I think I heard here, and I'm ignorant in the statistics and I'm ignorant in evolution. Whatever nature itself has been up to, this is it. Oh, I need to make some more of those weird things and improbable, impossible screwball life forms and landforms and everything that ever goes on. It's like, not done yet. We need to get more difference happening. Thank you, David. Thank you, all of you.
Thank you for that.
You're very welcome.
David Trafimow, I'm going to remind you that you promised us, and you're going to send me links, but send me the actual article. Otherwise, I have to go to Interlibrary Loan, but I won't share the article. I'll just share what I need from it.
Actually, David, it's in press, so you can share it. I'll send it to you, and anyone who wants to use the links, they're all in tables. Okay. And so all I have to do is go to the link and click on it, and you can go ahead and make progress.
Okay, I'll tell you what I want. I want the qualitative article. I want the article in press that has where to find these different measurement devices. And I want any other thing that you would share with us to help the organizational development audience. And I will redo it in the study guide. I'm going to edit this film. It's probably going to take me a couple of 20 hours and sort of get the word out. But thank you very much.
Pleasure, and I'll make sure that I send you. Thank you. So the title is Drawing Better Conclusions from Empirical Research, Pre-Data and Post-Data Strategies. Before getting into things, I just want you all to see a bunch of names. These are all but the last are mathematicians who have helped me develop the various things you're going to see. And the last one is a graduate student of mine, Kobe Wilson. Okay, so as most of you already know, the usual approach is to do a power analysis before data collection to figure out how many participants you need to collect. Then you do the study, collect the data, and then you do significance testing afterward. Now, there's a long list of problems with significance testing, which I won't go into now because if I do, I won't have time to go where I want to go. But I just want to mention that those problems transfer to power analysis whose goal is to increase the probability that significance testing will result in a statistically significant p-value. Like I said, I'm going to skip the problems for now and pretend for the moment that power analysis and significance testing are valid even though they are not. And my goal is to demonstrate that there are better alternatives. And the reason for this goal is several years ago, before I developed this stuff, people would tell me, oh, David, yeah, I get it. Significance testing is idiotic, but do you have something better? And I didn't really have something better, so I wanted to develop better stuff. Okay, so if we're not going to do power analysis and significance testing, then what? And I'm going to give you two non-traditional answers. There's the a priori procedure, APP, and gain probability, GP analysis. The APP is pre-data, and you might think of it as a replacement for power analysis. And GP diagrams are post-data, and you might think of them as a replacement for significance testing. To understand where I want to go, let's do reverse reasoning, because this will all be easier to understand in reverse than if we do it in forward order. So I'm going to start post-data and then move pre-data. So my favorite scenario is what I call a blood pressure scenario. But if you want to think of it as an intervention scenario in organizational psychology or just management, you can do that. The logic, I think, is going to be pretty obvious. All right, so imagine a gold standard study in the New England Journal of Medicine. The new medicine is being tested against the standard treatment for high blood pressure. It's a gold standard study, so you don't have to worry about the sample size not being good enough, that they didn't do random assignment and all that stuff. The means are in the hoped for direction. The difference is statistically significant, right? This is what you learn when you read a typical New England Journal of Medicine study. The question, should you prescribe the medicine? And the answer is that I have not given you sufficient information to answer. You don't need to know that the means are favorable and statistically significant. You need to know the probabilities of varying degrees of benefit or harm with the new medicine versus with the standard treatment. Okay, does that make sense to everybody before I go on? Normally I'm in person, so I can just look at your heads, but I can't do it now.
Yes, makes sense.
Thank you. Okay, so let's continue then. It seems obvious that we need estimates of varying degrees of benefit or harm with the new treatment versus standard treatment, so why don't we do it? And there are two answers. The first answer is that researchers may have been so satisfied with significance testing that they failed to see the obvious, or at least it seems obvious to me. Secondly, perhaps we did not have the mathematical advances to make such estimates feasible. However, reason one is simply a bad reason, and reason two, even if it was true, is no longer true. We now have GP analysis that provides such estimates. Now, before getting into the specific details, I want to talk about some implications that you should keep in the back of your mind as we go further. One implication, which is obvious, is that GP analysis provide much more useful information than significance testing. Implication two, if the goal post-data is to perform GP analysis rather than significance testing, then it is best to perform a pre-data procedure that fits well with GP analysis rather than with significance testing. Okay, so we've already got power analysis, which is designed to aid researchers in obtaining requisite sample sizes for obtaining statistically significant findings, but it loses all point if we switch from significance testing to GP analysis. A superior pre-data procedure aids researchers in finding requisite sample sizes to obtain sample statistics that are good estimates of corresponding population parameters. So that brings us to the APP. All right, so now that you have an overview, let's talk about the details of the APP, and then we will move to details of GP analysis. I tend to be a very philosophical guy, so let's be philosophical and ask, why do we collect a sample of participants instead of just using one participant? Right? It would be a lot cheaper to use one participant. Right? For organizational studies, it's a real pain to go to all these organizations and collect data. Why not just find one employee, ask your questions, and go from there? And the answer is that we want to be confident that the sample statistic that we calculate, let's say the mean, but it doesn't have to be the mean, is close to the corresponding population parameter, right? We want the sample mean to be close to the population mean, or that the sample standard deviation is close to the population standard deviation, and so on. Let me dramatize this by giving you Laplace's demon scenario. You have to understand that I'm a big drama fanatic in the sense that I love opera. Okay, so you're going to get drama now. Imagine that Laplace's omniscient demon, which means the demon knows everything, comes to us and tells us that our sample statistics have nothing to do whatsoever with corresponding population parameters. We would be in big trouble. We couldn't test hypotheses. Replication would be out of the question, and so on. Right? So it seems obvious when you look at it from a Laplacian demon standpoint that it's just absolutely necessary that our sample statistics are good estimates of corresponding population parameters. That brings up two more questions. First is the precision question. How close do we want our sample statistics to be to their corresponding population parameters? And there's the confidence question. What probability do we want to have of meeting the precision specification? We need to contend with these two questions in order to proceed further, okay? Let me give you an example. And don't freak out because there's an equation. I promise it's the last equation. I won't give you any more. But it's for those of you who have not had statistics, it's easy to understand. N, the lowercase n is the sample size. That's what we want to know. How big a sample do we need to collect in order to meet our specifications for precision and confidence? ZC is a critical z-score. So once you decide how confident you want to be, let's say 95% for a conventional value, all you have to do is convert the 95% into a z-score. In the old days, you did that by going to the back of your statistics book, and there would be a Z table, and you would simply copy the value out of that table. Nowadays, computers can do that for you. So that's the confidence part. The precision part, the lowercase f represents the fraction of a standard deviation we're defining as close. So for example, suppose that we assume a normal distribution and we want to know the sample size needed to have a 95% probability of obtaining a sample mean within 1/10 of a standard deviation of the population mean. Well, so the 1.96 you see in there is the z-score that corresponds to 95%. The 0.1 is the 1/10 of a standard deviation closeness that we want. And so the equation spits back the value of 384.16. However, people don't come in fractions. And so our convention is to round upwards to the nearest integer, which would be 385. Okay, so that's that's the actual simplest case that I can think of. And so you can see a little bit of the underlying math. Now, why does the a priori procedure differ from power analysis? And the reason for this is many times when I've talked to statistical audiences, they always ask, well, isn't this just another form of power analysis? And the answer is no. It is in the sense of it tells you your sample size that you need to collect, but it's not in the sense that the goal is different. It's different philosophically because of that. Remember, the goal of power analysis is to find the sample size needed to get statistical significance. Usually that would be p is less than 0.05. Right? So it's highly tied in with significance testing. The APP does not have that goal. Rather, the goal is to find the sample size needed to be confident that the sample statistics are close to corresponding population parameters. So it's completely different. Now, this philosophical difference leads to a mathematical difference as well. Power analysis is influenced by expected effect size, whereas the APP is not. And I'll show you that in the next figure. The APP is influenced by degree of desired sampling precision, whereas power analysis is not. And that's the second figure I'll show you. So here's a power analysis figure. And you can see along the horizontal axis that the effect size is increasing. And you can see along the vertical axis that the power is increasing. So as the effect size gets larger, you have more and more power. However, effect size has no influence whatsoever on precision, which is 0.28, no matter what in this example. Going the other way, now we have sample size along the vertical axis and precision along the horizontal axis. And you can see that as the degree of precision gets worse, remember 0.1 is high precision and 0.7 is low precision. As the precision gets worse, the sample size needed to reach it decreases dramatically. Okay, so let's really lay on the drama. Imagine a one-group experiment. According to power analysis, under the usual assumption of a medium effect size, only 13 participants are needed for power equals 82.2%, which is usually considered acceptable. But if you use the APP on that 13 participants, the precision is 0.54, which is awful, right? Think about what that means. That means that you're only within half a standard deviation of the, or even a little worse than that, of the population parameter. So I don't think anyone would want to settle for that in their research. I certainly wouldn't. Now, you may be thinking, okay, this is all nice, but researchers care about a lot more than single means under normality. Can we do other stuff? And the answer is yes. Here's a picture of skew normal distributions. The mathematics gets complex, so I'm not giving you that. I'm going to try to do this pictorially to make it easy. If you look at the pink curve, the lowest one, that's where alpha equals 0. Alpha is the shape parameter, and that's where you have normality. That it's useful to start from there so you can see that when the shape parameter is not equal to 0, whether in a positive or negative direction, notice that the curves get taller and narrower. We are going to exploit that later. So just keep that, try to keep a mental image of that picture in your mind. So let's consider a one sample case under skew normality, right? So you're interested, you have a single sample, but you suspect the population is skewed. Well, for skew normal distributions, rather than the usual mean and standard deviation for normal distributions, the mean is replaced by something called the location. The standard deviation is replaced by the scale, and there's the addition of a shape parameter. The location is obviously more appropriate than the mean if you have skew normality. And so we want to know the sample size needed for the sample location to estimate the population location at, and let's say we are going to use precision at 1/10 and confidence at 95%. Well, we have a program and we can make a graph. So here's the program. And the reason I'm showing you the program is even if you don't know any math whatsoever, you can do all of this stuff that I'm talking about because we have programs for everything. All you have to do is enter the skewness parameter in the first box, how much precision you want in the second box, and how much confidence you want in the third box. You click Update View, and you'll get a summary table, which gives you all the stuff you entered, plus if you look second from the bottom in the summary table, it'll give you the sample size you need to meet the specifications. And again, you don't need to know any math for this. Anybody can do that. Here's a graph that I made using that program, where you have shape along the horizontal axis and sample size along the vertical axis. Notice, let's look at the red curve first, and notice that as the shape parameter increases, that is, as you deviate increasingly from normality, what happens? You actually need less of a sample size. You need fewer participants in order to meet your specifications. If you look at the black curve, the same thing happens, it's just not as dramatic. Now you might be thinking, okay, that's nice for one group. What about two groups? What if you have the blood pressure scenario where we had the standard treatment versus the new treatment? Okay, so let's do it that way. Lots of examples. You might consider random assignments of participants to experimental and control conditions. Sex researchers are interested in males versus females. And I'm interested in people from Scotland versus people from England. Why am I interested in that? Because I saw a really nice exhibit of Scottish broadswords when I was in Scotland, and a person who worked there came up to us with an extremely gleeful expression on her face as she informed us that those swords were so sharp they could cut an Englishman in half. And she was very careful to specify an Englishman. So we were making jokes the rest of the day about how these are specialized broadswords, so you're safe if you're French or German or something like that. Okay, now suppose we do not want to assume the groups are normally distributed, but we instead wish to assume skew normality. And let me just point out that normal distributions are so rare that one statistician likened them to unicorns. So it's almost always wrong to assume normality, even though we always assume it. Okay, well, if we're going skew normality, then we're interested in the difference in locations, not the difference in means. So the question is, what is the effect of skewness on sample sizes per group and total needed to meet specifications for precision equals 1/10 and confidence is 95%? So the red curve is the total sample size, and the black curve is the sample size per condition. And you can see they both tell the same story, which is that as skewness increases, the necessary sample size needed to meet the specifications for precision and confidence decreases. Okay, so what are the implications of that? Okay, well, as an example, suppose you want to have precision at the 1/10 level with two groups. Shape parameter equals 0 implies you need 770 participants total. If the shape parameter is 0.1, very, very slight skewness, not much, it implies that you only need 300 participants. So just by having skewness that's so slight you would barely be able to see it in a figure, you get a 470 sample size savings, which is obviously huge. Another implication is if you want to exploit skewness friendliness, you must use skew normal, not normal statistics. You have to use the location, not the mean, the scale, not the standard deviation, and the shape. And you feature differences in locations, not differences in means. Oh, one other thing before I get to the next part, I want to stress something else. If you had the same experience as pretty much every graduate student in psychology for the last 40 years, then you're told over and over again that skewness is bad, and the smart thing to do is do some kind of transformation to render the distribution normal rather than whatever else it is with skewness. That teaching is very, very wrong. As you have seen, skewness is very friendly. It's not a bad thing. In fact, the worst thing you can do is transform your data, because then you'd have way less precision. If you want to maximize precision and minimize the necessary sample size needed to reach it, then you want skewness. It's a good thing to have skewness. So you shouldn't obey the graduate school teaching of get rid of skewness. You should exploit it. Okay. Now, one of the big brouhahas in the scientific literature, and this goes well beyond my area of psychology and many of your areas of organizations, is the replication crisis. In psychology, medicine, marketing, management, just about anything, there are many reports of systematic attempts to replicate studies failing. Now, I would argue that a major reason for our problems is that we depend on significance testing, right? In fact, that's the usual conception of a replication, is you get a significant effect, statistically significant effect, in the same direction twice. But if significance testing is invalid, why would you care about that? An alternative replication conception would be to get a similar effect size twice. But if the whole point of sample statistics is to estimate corresponding population parameters, what good is it to have two close sample effect sizes if they are far from the population effect size? The APP suggests a third replication possibility, which is that the goal is to obtain sample statistics that are good estimates of corresponding population parameters. So why not define a successful replication as when statistics from both studies are within the desired distance of the corresponding population parameter? Suppose the following is an example. Suppose you have skewness equals 0.1 in both groups. The desired precision is 1/10 and confidence is 95%. Your sample size per condition is 150, so your total sample size is 300. What's the probability of replication? Okay, pertaining to the difference in locations in the two groups. The obvious answer is that there is no way to know because we don't have the data yet. But there's a better answer. Since we set confidence at 95%, we know that we have a 95% of probability of being close. So you simply square 0.95 and you end up with 0.9025, which is close to 90%. So I would say that we have a 90% probability of replication. The example shows that it's possible to estimate the probability of replication without performing a replication study and without collecting any data whatsoever. It's simply a matter of performing the correct mental exercise instead of all of the incorrect ones that are out there in the literature. Now, an important caveat is that the example assumes an ideal universe where there are no systematic differences between the two studies, so only randomness is at play. In the real universe where we all work, there are systematic differences too, right? Different times, different days, different experimenters. The materials may even be a little bit different. So the calculated value should be thought of not as an exact number, but as an upper bound on the probability of replication. However, it's still useful because if the upper bound probability of replication is small, which it usually is, and I can direct you to a published, actually to multiple published papers that we have showing that, then it is mathematically necessary that the finding is unlikely to replicate. Hence, we have what many people think of as a replication crisis. If the upper bound probability of replication is large, then the finding at least might be replicable if the original and replication studies are sufficiently similar. Okay, now I'm not going to have time to go through all of this because it would take all day, but we have many APP advances. Means, skew normal, lots of different distribution shapes, difference in means with matched samples or independent samples, standard deviations or scales, proportions, differences in proportions, correlations, regression weights, contrast. If you have like a ANOVA design, you can use the APP for contrast. Maybe you have log normal distributions or gamma distributions, or maybe you're not interested in means or locations, you're interested in Cohen's D. So we can do that under normality or skew normality, coefficient of variation, medians, Laplacian distributions, Bayesian versions, and we're constantly inventing more stuff. Okay, so pretty much whatever you want to do, we have an APP program for you. So even if we stopped here, the APP justifies taking sample statistics seriously, even without significance testing, providing there's sufficient precision. But we're not going to stop here. This is only a warm-up. There's way, way, way more to come. So let's go post data. You've got your data. What the heck do you do with it? So at present, due to the dominance of significance testing, readers of journal articles get the following from typical randomized control trials in the social, business, or medical sciences. You get means, you get standard deviations, and you get either p-values or traditional confidence intervals, which are basically just mathematical operation on p-values, so not much of an improvement. The problem, as we already have seen with the blood pressure example, is that this is not what you need to know to make good decisions. You need to know the probabilities of being better off or worse off by varying degrees with the intervention, with the medicine, with whatever it is you're doing, than without, or than with an alternative. So GP diagrams are better, and I haven't given you specifics yet. We are now going to get specific. First, I want to mention that we have worked out the mathematics for skew normal distributions, which include normal distributions, delta log skew normal distributions, which include log normal distributions, and log skew normal distributions, skew t distributions, which include t distributions, and gamma distributions, which include exponential and chi-square distributions. We've been doing GP for a shorter amount of time than APP. So the list is shorter here, but it grows every few months as we accomplish yet another expansion. Nevertheless, even what we have here is probably sufficient for whatever most of you might need. So let me give you a medical example. And this is a real study with several thousand participants, and their p-value was way, way, way less than 0.001. So it's significant to what we might call the oh Jesus level. But it may be deceiving. So let's look at systolic blood pressure in Japanese participants, which is what Narita et al. Did in their 2020 paper. They found that in the summertime, the mean blood pressure is 131.1 mm, and in winter, it's 140.3 mm. If you compute a Cohen's d, which is simply the difference in means divided by the pool's standard deviation, you get 0.4, which is a respectable value. Now, they assume the data are log normally distributed, which is consistent with medical tradition. And after a logarithmic transformation, the p-value is way less than 0.001. Okay, here's the question I have for you. What I've given you so far suggests, yeah, season really does matter by a respectable amount. But does it really? Here's a GP diagram. And you can see what it gives you. The purple bar gives you, I divide it into purple bars and blue bars, and the bars represent the probabilities of being within range. Like how much of an advantage for summer over winter is there by between 0 to 10 mm of blood pressure? That would be the first purple bar. The other way is the first blue bar. You can see that they're about the same height and that the values are about the same. That those little numbers are representing the actual probabilities of being in range. If you go to the next couple bars, so just to the right of the first purple bar is the second purple bar, the probability is 0.096. The corresponding blue bar is 0.094, not basically the same. And if you go through the whole figure, you can see that the figure is just about symmetrical, which means that really the season doesn't matter whatsoever when it comes to, if you consider the probabilities of being better off in the wintertime or the summertime at varying degrees. So the significance and respectable effect size that we saw earlier are highly misleading. Okay, so we've seen how what seems like a good sized effect can hide that there's really nothing happening. Now let's go the other way. Imagine a scenario where participants are randomly assigned to a pro-exercise essay or a control essay, and hours of exercise per week are assessed. Let's suppose that in the experimental condition, the location is 5, the scale is 2, and the shape is 1. In the control condition, the location is 5, the scale is 2, and the shape is -1. Cohen's d would be 0, so there's no effect. And there's no statistical significance either, because significance is highly determined by the effect size, right? It's the size of the effect times the size of the study. And if the size of the effect is 0, then no matter the size of the study, you don't have significance. Okay, but GP analysis suggests something different. Okay, the first thing I want to show you is a program, so you can do it yourself. In the first box, you simply put the location, and this you get from your data. And almost any program, almost any spreadsheet or statistics program will give you mean, standard deviations, and skews. And we have a program which I can give you, that will allow you to translate those into locations, scales, and shapes. So the first value is the location, which is 5. The second one is the scale squared. Remember, the scale was 2, so squaring it is 4, and the shape is 1. For the second group, we have 5, 4, and now -1, if you remember from the previous slide. The harder part to understand is A and B. And to understand that, what the program does is it calculates the probability that Z is greater than 0, and it's based on a density curve for Z equals X plus AY plus B. So if you set A at -1, then you're in essence setting them equivalent, and B at 0, then essentially you're making it equivalent. So if you had the exact same conditions, your probability would be 50%, 0.5. Now you can see from the value of the table that it's 0.83, so there's actually a huge probabilistic advantage in favor that the study worked, despite the fact that the effect size, as we saw earlier, is 0, which shows you, I think, a huge flaw in the typical way of thinking about these things. Now, if you actually want to see a plot of Z, you can do that. Here's a plot of Z. Okay. It depends. If you look up high in that where it says table and plot, those are tabs. If you click on the table plot, you get the probability that Z is greater than 0. And if you click on the plot tab, you get this curve, if you want to see it visually. And you can see the curve. It's obvious that it's way to the right. You can see that the peak is way to the right of the 0 point. Okay, now what you can do then is you can vary the value for B, right? So you can say, well, since it's an exercise, an example, I'm interested not only in the probability of more exercise in the experimental or the control condition, I'm also interested in the probability of exercise by, say, between 0 and 1 hours more, or 1 or 2 hours more, and so on and so forth. And you can get all that simply by adjusting B appropriately. Okay, so what I did is, after lots of iterations of adjusting B appropriately, you can create this graph, and you can see that there's a probabilistic advantage of between 0 and 1 hour of 0.13 for the experimental condition to 0.087, we'll call it 0.09 in the control condition, right? If you want to go to 1 to 2 hours, it's 0.16 versus 0.05, and so on and so forth. You can see that this figure is extremely not symmetrical. In fact, the more extreme the amount of exercise advantage you care about, the higher the relative probabilistic advantage for the experimental over the control group. In fact, the experiment works extremely well, even though typical statistical thinking would have us believe that it did not work at all. Okay. I just said that, and I just said that. Okay, no point repeating myself. Yeah, apologies. I always get real excited about this stuff, and so I often forget to follow the slides. Let's do another example. Let's change the exercise essay statistics as follows. Let's say now the experimental condition location equals 6. The scale is 2 and the shape is -4.49. In the control condition, the location is 4, the scale is 2, and the shape is positive 4.49. Standard conclusion, Collins D is 1, which is a huge effect in favor of the pro-exercise essay. but a GP analysis suggests something different, right? And again, we're taking shape into account now, which researchers for some reason never do. Look at this. Now, the light blue bars are way bigger than the purple bars. In fact, although there seems to be a huge advantage in favor of the experimental condition over the control condition, you can see from the dramatic asymmetry in the wrong direction here that in fact the probabilistic advantages are way with the control condition over the experimental condition. So it's not just a matter of our effect size misleadingly led us to believe there's an effect when there really isn't. It actually leads us to believe there's an effect in one direction when the truth is very strongly in the opposite direction. Okay, so I think that's a really dramatic example of just how badly we can be misled by our standard statistics. Okay, and I just said all that already, so I won't say it again. Okay, well, maybe you're tired of skew normal distributions. Let's go to delta log skew normal distributions. Imagine a researcher collects diaries of negative thoughts in a control condition or a condition including a treatment designed to reduce them. Suppose the distributions in both conditions are delta log skew normal, with the following statistics following a logarithmic transformation, y equals ln x, right? We're talking about logs here, so you always have to do the logarithmic transformation before you calculate everything. Well, in the experimental conditions, suppose the location is 4, the scale is 1, the shape is 0, the proportion of zeros, remember this is a delta log skew normal distribution, so you can have zeros. The proportion of zeros is 0.3, 30, right? Control condition, location is 4, scale is 1, shape is 0, proportion zeros is 0.1. Okay, note that because the shapes are the same, probabilistic advantages cannot be attributed to shape. However, we're not done yet. First, let's go through the normal way of thinking. Cohen's d is 0. There's no effect going by standard thinking, and if you did a significance test, it wouldn't be significant. However, let's look at a delta log skew normal program. So let's start with the third box, probability of 0 observations in group 1. Right, so we got 0.1, 0.3. Then the mu really should be chi, but anyway, that represents the locations. The sigma squares are the squares of the standard are the squares of the oh no, I misspoke. Sorry, let me reverse. No, I forgot. This is log skew normal, so the mu 1 are sensible. Anyways, the sigmas are the squared standard deviations. Okay, and you can't see it, but you also have the shapes below that for each of the two distributions. So if the shapes are 0, then the mu's and sigmas really are means and standard deviations of the logarithmically transformed distributions, whereas if these are not equal to 0, then the mu is really not a mean, it's a location, and the sigma is not really a standard deviation, it's a scale, okay? The important thing to note is up at the top in the middle, the probability is 0.58. There's a probabilistic advantage in favor of the treatment group. You have a 0.58 probability of having less negative thinking. Okay? Again, despite the fact that the conventional effect size is 0. And here's a GP diagram that I made for you. So the reason there's a black bar is because since there are zeros, ties are possible, and there's a 0.03 probability in this example of a tie. But if you look at the negative thinking by between 0 and 60 minutes, your probability is 0.319 versus going to the big blue bar that and comparing it to the purple bar, 0.212, which is a substantial difference. And that difference maintains going to the next set. But I want you to notice that that the difference in the extremes is not as much as we saw earlier with the skew normal. Still, though, there is an obvious probabilistic, or I should say set of probabilistic advantages in favor of the control over the experimental condition, despite the effect size being 0. Okay, I said that. So summary. Do not use power analysis or null hypothesis significance testing. Use the APP to determine necessary sample sizes to obtain trustworthy sample statistics to estimate corresponding population parameters. And GP diagrams are way superior to significance tests for making informed decisions about what to do, which was one of David Boge's questions to start off with. So I'll give you the worse and the better inferential processes. The standard one and the worst one is to do power analysis, collect the data, do significance testing, and then decide what to believe or do. That's a bad idea. What you ought to do is the APP, then collect your data, then make a GP diagram, and then decide what to believe or do. And that's it. So I'll stop sharing.
Thank you, David. And yeah, stop sharing, and appreciate it very much.
Thanks. I'll stop sharing if I can figure out how to do that.